Hopefully this is pretty clear. Hello, everybody. Thanks for the opportunity to speak here at lovely Philadelphia. I'm talk to you about data center rack switch redundancy models. This originally was called top of rack switch redundancy models. I kind of renamed it last minute, a little more generic view. So my name is Dani Roisman. I work for Peak Web Consulting. We do network engineering and architecture. Previous to this, I spent quite a while, over 8 years, at Sony Online Entertainment, running the networks for EverQuest and PlanetSide, Star Wars Galaxy. It's how I met many of you folks. I'm going to be talking about, so at Peak Web Consulting, we do a lot of data center installations, data center designs, implementations, assistance, and we've run across many different ways of doing top-of-rack switch connectivity redundancy. So I realized that I needed some diagrams I can use to help show my engineers, my staff, my clients, here are all the different options we have available, and I figured if I really want it to be good, I should make it into presentation quality. And it just quickly led to something that I was able to present here. Now, we don't hear that many layer 2 conversations here, that many switching conversations. Although as network engineers, network operators, you got to switch before you can route. So hopefully this will be a little bit of a departure from layer 3 IP. Everything I'm talking about is agnostic, IPv6 and IPv4, and actually doesn't really even care. Although a few examples I only put IPv4 addresses, so apologies to the IPv6 folks out there. So server access, what are we talking about here? So enterprise content data centers, they have racks full of servers, usually Ethernet connectivity, and Ethernet switch is typically located in a rack to aggregate all the servers for that rack, and you need to go ahead and connect that rack to the rest of the core so these servers can communicate bidirectionally. Turns out lots of ways we can do this. Who's going to be interested in this talk? So any network engineer operator who's responsible for rack-based connectivity. What I'm going to show you will work from anywhere from one rack. I've deployed this to hundreds of racks in a single data center successfully. So anywhere between 1 to hundreds of racks. You could even extrapolate this to thousands of racks. I just haven't had the luxury of doing so. Anyone whose job relies upon having undisrupted access to these servers might want to pay attention. Maybe you'll learn something new. Maybe you'll find something that I've done that you didn't like, or maybe you want to tell me about something that you've done that I haven't covered. I'd love to hear about it. And many folks are really battling with, well, how do we do it right? How do we do it in a way that we save costs? How do we do it in a way that we don't melt down the network when we make changes? So there's a kind of a stability versus redundancy versus failover time versus maintainability trade-offs. Here's our sample network. Very simple. You have a distribution layer. If you're small enough, it may be a single pair of chassis that are doing your eBGP and your iBGP and your OSPF and maybe some WAN links. In larger environments, you have this kind of a pod architecture. You're rubber stamping throughout your data center. But usually there's at least two switches that are connecting to a rack. You can call them a distribution or core layer. And in a single server rack, you have some number of servers connected to usually at least one switch, sometimes maybe more than one. And oftentimes you want to connect them to your distribution layer with at least 2 links for redundancy. So this is kind of the base diagram, and you'll see multiple iterations of this throughout the talk here. This talk is actually a little bit long, so I'm going to zip through some of these more verbose slides. They're on there for the benefit of folks who might download this later and want to understand a little more what I was talking about for some of the more newer people into the network world. So I'm not going to walk through all of these more verbose slides. So the model 0, the no redundancy model. Very simple. You got one switch, one rack, one distribution layer, and you're set. This will work. You pass packets, no problem. This will work forever until you have a failure in any one of these locations. So obviously this is not going to get you redundancy, but it'll get you some good connectivity. There's what I call a model 2.5. This is a manual activation of redundancy. So here you went ahead and you connected to your second distribution layer, but you severed the link to the second layer. Maybe because you don't trust your distribution, you don't trust your redundancy, you're afraid of spanning tree loops. So really simple, you come back, you plug it in, layer 2, you VLAN to your rack, and you say, oh, I'm afraid of loops, or one time I had a problem, so you shut down one of the uplinks. So if you have a failure on the primary link, you're going to go ahead and you're going to have to manually unshut the second link. Now do yourself a favor, if you're going to run this model, shut it up at the distribution side. Don't shut the backup link on the rack switch side, because then you can't unshut it without walking up to the rack switch or consoling in. Do yourself another favor. If you're going to switch over, make sure you shut down that primary, so if it does come back up, you don't have an inadvertent loop. Now do yourself a third favor. Just don't do this. It's messy. It's manual. I have seen it before, but nobody likes to be woken up at 3 o'clock in the morning to actuate a backup link. You want something that's a little more automatic here. So the first model here, this is the cliche. This is layer 2 in spanning tree. I'm sure we've all seen it. Very simple. You create a loop within your network. You make in the simplest form, you make a triangle between 2 distribution switches and a rack switch. You have your VLANs available on all ports. And if you're doing it right, you're going to give yourself a nice low priority on your primary route that's designated as one of your distribution devices. And you're going to have a slightly increased priority, maybe 8K versus 16K for your standby route. And your rack switches, a little hint here, you're going to want to go ahead and set them lower than the default 32K. I like 40K. It's a nice number. And once you plug all this in, if everything's working properly, spanning tree is going to go ahead and block towards the backup route. And the loop will be broken, and everything will work just fine. In failure mode, if the primary link gets severed, spanning tree on the rack switch will go ahead and detect I lost my primary path, and I'm going to go ahead and unblock on my secondary path. And of course, when the primary path comes back up, spanning tree is going to recover and say, great, wonderful. It works really well. It's extremely common. It's pretty easy to understand. As long as you don't read the docs too much and get your head in the state machine and the BPDU types and topology changeover, it kind of just works, usually. It's really easy to verify that your backup connectivity is up. You go to your rack switch. You look for blocked ports. As long as you're blocking towards your backup, that means A, you got a route that's not alive, which is great, and B, you have an available backup path. With some of the newer, with the more advanced spanning tree implementations, you'll even see alternate path available. It's pretty flexible. Any subnet can be extended to any rack in your data center via VLAN tagging. This is really great for server mobility. So in the virtualized world, we find ourselves needing to move servers from one rack switch to another rack switch, from one physical server to another physical server, moving our VMs around. We don't want to do renumbering. We don't want to do re-VLANing. It's really nice and mobile. It also allows for your centralized services. So you may have a server load balancer, a firewall that's acting either in a transparent mode or in some other layer 2 mode. He can be plugged right in there at the distribution layer, and his internal VLANs can be extended to any rack switches. It also helps conserve public IPv4 address space. So this means that if you are doing public IPs to your servers, you may designate a /25 where the public IP is on a VLAN, extended to all of your rack switches, and you can fit as many servers as you can squeeze in that /24. There are no physical limitations, physical topological limitations. One of the drawbacks, or many drawbacks, of the layer 2 and spanning tree. So the stability of your spanning tree really varies based on not only which vendors you use, if you have a multi-vendor environment, but in many cases even the model of switch that you might have, the family of switch from a specific vendor. As I said, multiple vendors. Some vendors have proprietary add-ons to spanning tree, which work really well. Some vendors won't provide that. And if you have a multi-vendor environment, you may want to work with the least common denominator. It's going to reduce some of your flexibility. If you make a configuration error, a cabling error, even a hardware failure, CPU overrun, this could cause an entire network to shut down. And I'm sure many of you have experienced this. I know I've seen it many times. I know I've caused it a couple times in my earlier days. And I always tell my new network engineers, you will probably take the network down within your first few months. And it's okay if you do it once, just don't do it twice, please. Network troubles in a spanning tree environment can be very difficult to trace, to track down. There isn't a lot of data available in the spanning tree environment. You can't just say, show me broken loop, enter, and it'll show you where the problem is. It heavily depends on your rack switch CPU health. So at this point, when you do this, your rack switches are the ones that are taking care of blocking. So you have 100 racks. You have 100 different places that need to block. If one of those rack switches gets overrun somehow, he can't process those BPDU packets, those spanning tree signaling packets. He might fall back and just unblock because he didn't hear BPDUs because he couldn't process it. Oftentimes, if you want better failover performance, you want better stability, you may need to actually do additional tweaks, maybe adjusting timers, maybe configuring. Some vendors have extra add-ons, like I said, uplink fast backbone, fast root guard, path guard. You also are going to want to designate edge ports versus point-to-point links. And in the typical spanning tree environment where you're blocking all traffic on a single link, you may not be able to use that backup link. There are variations with PVST, with MST, where you can designate some VLANs here and some VLANs there. It gets kind of messy. the rule of thumb for me is a backup link's a backup link. I never use it. So in this case, you're really not going to be able to take advantage of that extra capacity. So in some people might say you're wasting ports. Model 2, this is a full layer 3. And this model is also pretty simple. Your rack switch is running the layer 3 protocol. He is the default gateway for your servers, is the actual switch located in that rack. You then have 2 uplinks to your distribution layer. You number them in some /30 routing segment, and you run some flavor of IGP. You can even run IBGP, EBGP if you want, some routing protocol between your rack switch and your distribution layer. Works pretty well. All servers in your rack are exclusively numbered. I'm going to tell you more about that in a moment. Distribution switch, I said they're point-to-point links. You're running layer 3 protocol. Benefits of this, pretty simple to understand. Nice and simple layer 3. There are no layer 2 loops, no spanning tree to worry about. It works very well in a managed hosting environment. We have a lot of small subnets for customers. Maybe customers may get /30s or /28s, and they have a few servers in a rack. It's very robust. If you do make a configuration error, usually the worst case you're going to do is take down a single rack. It's near impossible to take down an entire data center based on a single configuration error in a layer 3 environment. It's very easy to verify your backup connectivity. You just go on your rack switch and look up the routing adjacencies, or go on your cores and look downstream at your routing adjacencies. If you have an adjacency, chances are that link is pretty healthy. This also supports multipath on your rack switch, so you can take advantage of that backup link. So if you're announcing default to your rack switch on 2 links with the same cost, many devices will simply load share across those 2 uplinks. So you're actually utilizing your backup capacity while it's available. So drawback here, number 1 drawback, and people are watching the bottom line, this significantly increases the cost of your rack switches. You need to be able to run a routing protocol. As Steenbergen said on Sunday, if we can just decide that RIP v2 is going to die, that's usually what you get for free, is some flavor of RIP. Many environments, if you want to run OSPF or BGP, you're going to pay extra, either a licensing fee, sometimes an actual hardware key you need to apply on the rack switch. The racks have to be exclusively numbered. I mentioned that in the diagram slide. What that means is that this one rack is given this /24, let's in our RFC 1918 world, and that /24 can't exist in any other rack, which works if you're all running RFC 1918 in your data center, because RFC 1918 is free. The downside of being exclusively numbered is you can end up with inefficient use of IPv4 address space. Let's say you're running public IPs. You decide this rack is going to get this /26 worth of address space, and he's locked down to that rack only. Well, if you only have 40 servers in that rack, you're wasting 21 public IPs. And that's really not responsible. So you're stuck in an environment where, well, I can use 13 public IPs or 29 public IPs or 61 public IPs per rack. 13 is pretty small for most of us. 29, if you have 22 servers in the rack, that's pretty decent if you're running a typical data center environment. But if you have a very high density environment, or you have blades or whatnot, you might find that you need more addresses than that. So that's when I say the exclusive numbering may be a problem for you. The other problem with exclusive numbering is relocating a server, physical server, or a VM from rack to rack means that you need to go ahead and renumber. Because you can't just take an IP address and move it to another rack, because the default gateway is locked down to that initial rack. It also limits your NIC teaming abilities. And I'm drawing a blank on why I put that in the slide, but we'll get to NIC teaming later. Additional services in a layer 3 environment. If you have SLB firewalling that wants to be running transparently in layer 2, or wants to be doing proxying back towards the server, you now need to deploy it in a layer 3 environment. You can't, your load balance and your firewalls can't enter into the server-based VLAN. They need to be off to the side, and maybe you need some PBR tricks or some other routing protocol running on the services modules or service appliances coming off the side. So Model 3, this is kind of a mix and match where you decided layer 3, I'm okay with all the drawbacks, but I just can't afford layer 3 switches in my rack. So this model isn't very obvious to people, and I find myself having to explain it a couple times, so I figured I'd detail it here. So the rack switch is an inexpensive layer 2 rack switch. It can even be unmanaged, although I don't recommend it. I do like having an IP address in my rack switch so I can do SNMP monitoring, temperature, power. I can log into it if I need to make changes. But in general, you have a dumb rack switch. It's layer 2. He has 2 uplinks to distribution layer. Excuse me. The distribution layer, his physical ports are layer 3 ports. So it's a routed port facing the rack switch, and between the distribution layer, you're running some kind of HSRP, VRRP, some next hop redundancy protocol. And the default gateway for the servers is now at the distribution layer. And typically it'll be on one distribution switch. If you want, you can run multiple default gateways and alternate if you want to try to utilize both uplinks. Again, all servers have to be exclusively numbered. And the distribution switches will then go ahead and announce the subnet for that rack into IGP based on physical interface link state. So I'm going to zip through some of the detailed slides. So in the way the redundancy works, you have your uplinks running just fine. Everyone's working wonderfully. Let's say a link is severed. What's going to happen is if a link is severed towards distribution switch number 1, distribution switch 1 will realize, well, my link is down. So I'm going to go ahead and I'm going to withdraw the reachability from the IGP because my physical link in that subnet is down. The redundancy protocol between the two distributions is going to fail over. Usually it's a time-based hello failover, and distribution switch 2 is going to take over for the default gateway, and everything continues as normal. There's a brief hit, anywhere from fractions of a second to maybe up to 2 seconds, depending on your next hop redundancy protocol, depending on the routing protocol you're running within your environment, but it works pretty well. When you restore connectivity, excuse me, restoring connectivity usually is a zero-hit operation. Everything returns to normal. If you're running preemption, maybe your next hop redundancy fails back. But either way, it works very nicely. The benefits of this model is, again, no STP, no layer 2 loops. You don't have to worry about taking down your whole data center if somebody plugs in a wire incorrectly. Lower cost in the full layer 3 model because the rack switches are layer 2 only. In some cases, can be extremely inexpensive rack switches. It could actually even be less expensive than the STP protocol. It can be multi-vendor. It can be a $45 you bought it at Fry's switch even works. Again, I don't recommend that. I like being able to reach my switches. One of the drawbacks, of course, as we said with layer 3, you need exclusive numbering. So one subnet is locked to that rack. So you're also going to get IPv4 inefficiencies. You can't use the upstream backup link capacity from the servers to the distribution unless you're running additional configuration. You may have 2 VRP IPs with alternating servers. There is a proprietary GBLP, which alternates MAC responses. There are fancy ways to get around it. Again, I'm a keep it simple, stupid kind of guy. You just can't use your backup in the upstream direction, although you can use it down towards the servers. This may impose multi-netting. If you come back and you say, you know what, I actually want to have a few different subnets in this rack. Well, since you only have one physical interface, you may need to do multi-netting, have multiple subnets available on that interface of distribution. Otherwise, you can also get around that by doing .1Q sub-interfaces, layer 3 sub-interfaces down towards your rack switch. This is not very common or straightforward. I find that I have to explain it multiple times to people, and they just don't realize, oh, well, it's layer 3, but I got a layer 2 rack switch. So one of the downsides here is that you might have to take some extra time with training. You might have to re-explain to your management or to your new engineers kind of how it works. Next model here is link failover. This is a kind of interesting one. I've deployed this in one single very small environment. I mean, 2 racks of small environment. I haven't deployed it in a large environment. Very simply stated, your rack switch is running some type of link failover protocol where when you configure your rack switch, you identify one port as your primary and the other port as your backup. And as long as the primary is up, no traffic is switched to the backup. This is a layer 2 model where you have you are almost creating a loop of VLANs, but you're actually relying upon a different type of protocol to block that loop. Many vendors support this. I'm going to just telling you the 4 that I personally spend a lot of time working with. If you're not included here, my apologies. It just means that I haven't worked with your product that much. But I need to give you these names because these are kind of hard to find in the docs, and you need to want to know the specific name. Cisco's going to call this a flex link. Foundry's going to call it protected link groups. The EX series of Juniper calls us redundant trunk links, and Force 10 calls us redundant paths. In the Force 10 Cisco world, it's also called switch port backup. The way the redundancy works, if the primary link is severed, the rack switch will detect I lost my primary link, going to go ahead and switch traffic up to the backup link, and all is wonderful. One of the benefits is we're not relying upon the health of the switch. He's not relying upon BPDUs being processed and timers expiring. It's pretty simple, binary. If link up, link down. If link down, link up. No complex state machines that all the different various STP protocols have to offer you. During a steady state, there is no loop. The backup link is never passing production traffic. It may provide rapid failover in certain conditions. Link goes down, link goes up. It's actually pretty quick to detect that. there is reduced interoperability concern. So if the rack switch provides this feature, you're really not concerned about what vendor, what special tweaks. You're not even concerned about what you're running in distribution layer as long as the rack switch provides this feature. And it has the same server mobility, same IPv4 efficiencies as typical layer 2. All VLANs to all data, all VLANs to all racks, if you so decide. And one of the drawbacks of this link failover, with some of the vendors, the backup link is actually in an actual link down state. The problem with that is you can't confirm if it's plugged in the right place. You can't guarantee that there is a backup port available, because when you do a show in status, show in brief, you're seeing, well, the link is actually down. You also can't always map the backup interface if you don't keep very good documentation of your network and you're relying upon things like LLDP or CDP or FDP. Well, you can't map those backup links because they actually show as down. Also, with a physical link down, you may find there's delays in failover due to spanning tree that may be running on your distribution layer. Spanning tree is always a great idea, in my opinion, to turn on as a safety net just in case, even if you're not intentionally putting up loops. And what will happen is, when you have a primary link goes down, second link comes up, you may actually have a time delay before forwarding occurs from the distribution switch down to that rack. So having the lack of any kind of protocol running between the rack switch to the distribution layer is going to limit the knowledge of your redundancy. You may even have some unexpected surprises where your backup link never got plugged in or got moved and that new cable wasn't working right. Pin 1 wasn't fully crimped in. You can't load balance in this environment. Typically, again, there are a couple proprietary exceptions that I recommend staying against, but primary link up, backup link down, completely unusable. And with some vendors, when you turn on this protocol, spanning tree is actually disabled on the uplinks. Well, you got a problem there. I said you need spanning tree to protect against inadvertent loops. And in fact, if you have two rack switches, with one vendor, you have two rack switches, you have this protocol configured. If you accidentally run a wire between those two rack switches, you will create a spanning tree loop, which will go undetected and go unblocked. So you need to watch out. There is a downside to this. Question, show of hands. Is anybody using link failover in production? Anybody really using it for more than one rack? Okay. Don't answer, but start to think about why not. And if you have a reason why not, if you ran into troubles, I'd love to hear about it. This isn't as flexible as spanning tree, of course, but in my mind, I think it provides exactly what we need. In your typical rack switch environment, I have two links. I don't want traffic on the backup link unless the primary link goes down. To me, it seems almost perfect. But I've never seen it in production. I said I've run it in a very small environment. I've personally shied away from it because I haven't seen it often. I haven't seen it mentioned often in documentation. I haven't seen it shown in examples, and I'm wondering what's the problem with this? How come we're not using it more? Other than, like I said, this weird kookiness where spanning tree may get turned off on those links. So if you have some feedback, I'd love to hear from you. Why aren't you using it? Have you considered it and shied away from it? Have you never heard about it and said, "Wow, this is remarkable"? Because when I heard about it, kind of opened my eyes, but I haven't quite gotten around to committing to deploying in a large environment. The next model here, this one's kind of interesting. I call this layer 2 distribution with layer 3 rack switches. My friends at Woven Systems, you don't hear from them too often, but they helped me develop this model. They were trying to pitch into a 200 rack data center, trying to replace a very intelligent layer 3 core with their very robust, very inexpensive, and simple layer 2 core. So in this model, we'll walk through this a little bit more. The distribution devices, two separate switch fabrics. The rack switches form IGP adjacencies with all the other rack switches and the cores. You could use inexpensive, unmanaged distribution switches. Again, I always recommend putting managed switches in there so you can monitor your network and respond to any issues without walking up to the switch. The server rack, you have a layer 3 rack switch. That is the server's default gateway in the typical layer 3 environment. He's the default gateway for the servers. And he's forming adjacencies across two diverse subnets, what I call the green and the red here, distribution routing 1, distribution routing 2. The default gateway, we'll need to slide. Showing you an expanded slide, what does this really mean? Because I showed the first slide to a couple of people. I'm like, well, I don't get it. This looks like your other slide. So showing you what this looks like, hypothetical 4 racks here. So you have 4 racks here. Each rack has a layer 3 rack switch. Each one of them is plugging into this 2 different layer 2 flat VLANs. And they're all forming an adjacency over, let's talk about OSPF, just one very large broadcast OSPF, two large broadcast OSPF subnets. It's actually kind of interesting. Again, people don't seem to be using this that much. There may be some scaling concerns, I understand, but it's actually kind of neat. I actually do have one production environment running like this with about 20 routers speaking together. This has all the benefits of full layer 3, no loops, no spanning tree. You can utilize redundant uplinks because you're doing equal cost multipath. You can, during steady state with all physical links up, you can actually spread your load, which is really nice. If your application or your product requires layer 3 access devices anyway, you can actually get some economy by putting in some low-cost layer 2 switches. For example, if you're maybe an ISP environment, not as much rack switch, and you're providing layer 3 access, you have a whole bunch of T1, T3 routers, you already need that layer 3 access, you don't necessarily need a very smart layer 3 core in there. This introduces kind of a novel any-to-any routing over layer 2. So rack 1 needs to talk to rack 3. Well, they have direct adjacency. They just switch it over that layer 2 core. Drawbacks. Just like the layer 3 model, you need more expensive rack switches. You also need exclusive numbering, which means a subnet can only exist in that one rack. And of course, if you're running IPv4, you have inefficiencies. Since uplinks aren't actually point-to-point, you're not going to have an immediate failover based on link failover. So if switch 1's uplink 2 goes down, well, switch 3 won't actually know about it until some kind of keep alive or timer expiration on the routing protocol. This model is not very common, not very straightforward, so again, you're going to spend some extra time describing it to people, preparing your staff to support it. The last model here, this is a server-based model. This is where you have multiple NICs in the servers. This one, many people know and love it. This is called NIC teaming, NIC bonding. So the server itself has 2 uplinks to diverse rack switches. Those rack switches each have diverse uplinks to different distribution devices. Very simple. There are no loops. Or there are no loops in the network model. You're placing the redundancy burden on the servers themselves. You supply your 2 rack switches for server access. This is very common when you're using blade chassis. And there are different methods available for the servers to determine whether or not the primary backup link is alive. The most simple way is just check the phi for physical link state. You can also be running ARP queries from the server. You could be running ping the default gateways, and the server can make sure that both links are actually functional all the way to his layer 3 device. Excuse me. The way redundancy works, you have a server with dual uplinks. If the primary link is severed, the server will realize, in using one of the previously mentioned methods, that the primary link is no longer available. He's going to shift all his traffic to the alternate link. In another model, another failure scenario, let's say you lose your uplink between distribution switch 1 and rack switch 1. Well, you need a way for that rack switch to signal downstream to the server that, hey, I lost my uplink. And that's typically using link tracking, saying if my uplink goes down, I'm going to shut down all the links facing my servers. If you don't have it available, there's an extra delay where the server might have to realize I can no longer ARP on this NIC for my default gateway. Either way, the server should somehow detect that something upstream went bad on NIC number 1. He'll shift over traffic to NIC number 2. Benefits here, again, it works with pretty much any switch in the rack. If your budget's tight, you can shift some of that money out of your intelligent rack switches and move it up to your core distribution or border where you might need it more. You have the same layer 2 flexibility as typical layer 2 models, because you really are extending all VLANs to all rack switches if you so desire. The network itself requires really minimal attention. This is really good for organizations that are very sysadmin heavy. They want to do more work on the servers, and not very network engineer heavy. They don't want to spend time babysitting the network. They want kind of a bulletproof, surefire network, which doesn't run layer 3 protocols, doesn't run spanning tree. The network, as I said, has less risk of failures due to routing protocols. I've definitely seen this where they don't want network engineering. They want the network to be a black box, plug in the wire, it works. We know how to run servers. We have our Puppet, our CF engine, etc., and we can manage servers en masse this way. The downside here is it increases your server complexity. So now if you do have a couple thousand servers, now you need to make sure that all 1,000 servers know how to use primary, secondary link, and they're monitoring properly. There's no good centralized way of saying, yeah, I have redundancy. My primary link's up, my backup link is down. You can't just go ahead and query your core or query a handful of rack switches. You now need to query every single server to make sure that second link is usable if you're trying to ensure 100% redundancy. Of course, this burns 2 NICs per server, so twice as many. You need twice as many NICs on the server. If you have an environment where you have a front-end NIC and a back-end NIC, well, now you got to add 2 more NICs for dual front-end and dual back-end. You're going to want to have a way to signal the servers if the uplink from the rack switch failed. And redundant capacity, if you configure the way I recommended, which is active backup, your server is only sending traffic on one NIC and only run rack switch. So you have this extra rack switch which just isn't being utilized that you paid for. A couple little extras here. Most of the failover schemes, they rely upon link state detection, port up, port down. Sometimes it's not properly reported. Sometimes there may be a delay. There are some other additional protocols that we're running. Very simple remote fault signaling, and that's usually part of a gig negotiation, 10 gig negotiation. You can run UDLD. UDLD has some stability concerns, different vendor implementations, works, doesn't work, interoperabilities between vendors. One vendor, you run a UDLD, it works just fine until you go ahead and run a very CPU-consuming VTY command, all of a sudden your UDLD flaps. Unfortunately, I've seen it, and it's hurt very badly. BFD is supposed to be the silver bullet for this. BFD is great. On paper, sometimes it even is performed in the ASIC, supposedly. Implementations are still few and still having problems. It'll be great when we can all use BFD universally. There are a couple models that are coming out that I didn't show here because I personally haven't really touched them, so I can't speak authoritatively. Some of them are based upon where you run link aggregation on the rack switch to diverse equipment at the distribution layer. You can do it in the case of a stacking switch, and you run to two different members of the stack. There's something called multi-chassis link aggregation. Cisco calls it MEC in the Cisco VSS. There's Cisco Nexus, something called VPC virtual port channel. There are other vendor implementations. I didn't take too much time filling up a slot with everybody else's names, so sorry if I didn't cover you. The ink is still drying on some of these alternates. As soon as I deploy them, I'll come back and tell you guys about them. So in summary here, there's a quick quote I picked up while I was doing this. I chanced upon the Cisco data center design. It says, a routing protocol identifies where to send packets. Spanning tree identifies where not to send frames. You can go ahead and download this PDF, and the link is here on that full document. It's an interesting document. I personally, and here at PeakWeb, we've deployed and operated all of these models over the past 10, 12 years with success, failures, really different data center environments, different applications. There is not one final golden solution. It really is application dependent and topology dependent. I think, and I'm wondering if the layer 2 model is actually coming back because of vMotion, VMware, the ability to move, the desire to move virtual machines without renumbering from rack to rack. Maybe where previously layer 3 was the golden ticket, and now, wow, I need this layer 2. So I'm wondering if spanning tree is coming back. And that's all I had. So thank you again very much. If there are any questions, I think we have a few minutes.
Absolutely. Let's take a few minutes.
Thanks,
I think this is a hot topic, and there's a lot of new stuff that's going to be coming out in the next few years in this area. So, questions?
Hi. I guess I'd like to present one slight twist that I've seen of maybe the last model where you
Hi, Avi Friedman from Akamai.
Thank you, Dani Roisman from PeakWeb. Where the end hosts are actually running an IGP. So you actually dual attach them, port channel, it does burn links, but if you're going to have active backup anyway, I've seen that in even simpler topologies where you actually attach the host to two big catalysts.
Yep.
But you could also do that with either layer 2 or layer 3 switches in front. It requires a certain amount of rigor in your configuration management, and a lot of people don't want to actually run IGP on the end hosts.
Yep.
But it makes it very easy to grab the machine and take it and put it somewhere else in the infrastructure. So
yeah, you can definitely run /32. You can definitely run /32 on an IGP, the end host, and it gives you wonderful mobility. Like you said, the administrative burden on that is extremely high. The impact to your IGP can also be pretty high. Now you're carrying around a lot of /32 routes. Yeah,
it's also cool for any cast. Hi, Jake Kuhn, Green Hills Software. Do you happen to have any quantitative data to compare top-of-rack switches against, say, first cabinet row switches, and comparing cost of operations against cost of build-out and complexity?
Unfortunately, I don't have any really good numbers there. End-of-row switching is another viable model. I tend to shy away from it. But I've seen it done. It definitely works. It's more wiring. It's more expensive chassis typically, but it's a very viable model. But
How about
it's,
from redundancy standpoint on a per chassis basis?
so of course the downside with an end of row chassis is your fault domain. So now you need to do a maintenance on a chassis, you're going to lose that entire row. So I like to spread the fault domain. There's also there is a cost of acquisition. If you're building out a full row and you're only populating the first rack, you got to buy that first chassis, associated management modules, whatnot, even for the very first rack. If you're doing in-rack switching, middle of rack, not top of rack switching, but if you're doing in-rack switching, you have a fixed incremental cost for every rack you add.
Okay, so you might want to add something in your presentation about redundancy on a per chassis basis of top of rack switches, because generally speaking, with some exceptions, top of rack switches are workgroup switches with only single power supplies, for instance. So now you've got the inability to do redundant power on them, and there may be some design trade-offs that you have to make, or design workarounds at the server level to take that into account.
Yeah, absolutely. To be fair, I probably should start with the fact that this is kind of more of a back and forth on the title. The title really was top rack switching. So there are other alternates, but I was just focusing on the top rack switch options. So not wanting to introduce another variable that to say that you can also do end of rack switching. But thank you.
Thanks for the presentation, Dani. Anton Capella from Voxel.
Howdy.
And the one question I was going to ask to you, was since you represent so many edge cases for where this stuff really isn't very important, have you had occasion to ponder why there's no equivalent to HSRP or VRP or whatever, which doesn't burn accessory addresses within the layer 3 attached domain? I just have to wonder, at some point, is this actually going to be worth asking a vendor for, or have you had occasion to consider that? Or if you have, what have you come up with or considered or thought about that?
So you mean where you're not burning 2 extra IPs?
Yes, sir.
No, you don't have to. We've done it. We actually have an environment where we do this. So what you do is the physical interfaces get numbered in some other subnet. So let's say you're using burning RFC 1918 for the physical interfaces, and the only real IP is the HSRP address.
Sure. So last time we tried Cisco Standby with this, it seemed to be not present in 12.2 or 12.1. Are you doing something cool?
Yeah. Okay. So.
Tell me later. Thank you.
Okay, there's believe it or not, it worked in older versions. In 12.2.40 they shut it off, so the secret is the real standby IP address is part of the fake IP, and you do a standby secondary with the real IP address. There is a workaround.
Igor, if you could go, and then if the rest of the questions, if you guys could find Dani at lunch.
I was just going to say, I'm leaving at 4 p.m. today, so find me at lunch or email me. Unfortunately, I have to cut out early today. But if you find me before then, yeah, or email
me. Igor with Yahoo. We run well north of 10,000 rack switches, and I wanted to offer some caveats to some of these options to watch out for, because we've tried just about every one of these and with varying success. First of all, to option number 2, where every rack switch is layer 3 adjacent to the core. With the larger size cores, you may find that your cores can't hold this many adjacencies. We've seen some spectacular core meltdowns when the number of adjacencies started to reach about 400. Similar thing goes to option number 3, which you said isn't very common, but I can tell you it's incredibly common. We've seen where core switches decided to peer up through the rack switch. Be very careful of that, because 400-way ECMP across gig links doesn't work so well. As far as when it's a very the address burning problem is a very big one in a layer 3 type deployment, because most top of rack switches are 40 ports, 48 ports, so you're going to be wasting a lot of IP addresses. And finally, you were mentioning the Woven model, basically, where you have the layer 2 distribution, and then you have the layer 3 rack switches that are all peering up against each other. If you think the CPU of those little rack switches can actually handle that at scale, you may be in for a very big surprise.
Yep.
They break very, very, very quickly. Despite the DR and the BDR, you're going to need something beefy to be the DR and the VDR if you're going to do that. So there's just some feedback.
Yeah, absolutely. The caveat on that one, Igor, is that you want to go ahead and set your rack switches to OSPF priority 0, so they don't actually take over DR, and you need a beefy box to serve as your core. Absolutely. Yeah, thank you. Okay. Thank you all.
Thank you, Dani. Good presentation. So we have a